Greetings and welcome to the lecture notes for what I call Chapter 6, Part 2 of Chemistry 221. In Chapter 6, Part 1, we looked at the three first quantum numbers, NL and M sub L, and we also talked about the history and the development of how the idea of orbitals in subshells and shells were developed. In Chapter 6, Part 2, we're actually going to place the electrons in the orbital, and if Chapter 6, Part 1 seemed a bit weird, a bit esoteric, as we talked about quantum numbers, disallowed, and nodes and stuff like that, I'm hoping that Chapter 6, Part 2 becomes more real. If you've taken a chemistry class before, you've probably seen electron configurations listed as 1s2, 2s2, 2p6, that kind of thing. And that's where we're going in this section right here. We're going to see how all these quantum numbers led to the development of electron filling order. So without further ado, let's check out this section. We saw in Chapter 6, Part 1 that when electrons are placed around atoms, people can use quantum mechanics and do some kind of crazy math on it. We won't do the math, but we will look at the results of the math. And from the math, we saw that there were shells, subshells, and orbitals. And shells get the symbol N, sometimes called the principal quantum number, L, the subshell, sometimes called angular quantum number, and the M sub L is the magnetic quantum number. In an atom, the punchline of the next several slides is that we're going to see that each orbital, which is where the electrons hang out, you can only have 2 electrons per orbital, okay? This is kind of the punchline of what we're going to start talking about. I use the analogy that, and I talked about it in Chapter 6, Part 1, how N is kind of like a street and the L subshell is kind of like a house, and in the subshell there are orbitals or rooms, if you will. And now we're going to talk about putting people in the room. And if you have to, you can put 2 people in a room. And that's similar here, but silly, of course, for how electrons go in orbitals. You can only have 2 electrons per orbital. The reason for this has to do with the 4th quantum number, which is called the spin quantum number, M sub s. And we didn't really talk about this in Chapter 6, Part 1. But in Chapter 6, Part 2, that's going to be really heavy. Now, M sub s didn't come out of the initial math on these things, believe it or not. M sub s wasn't seen. However, what happened is the guy in the right corner there, Paul Dirac, he combined relativity, which was Einstein's thing, with quantum mechanics. And when he did that, the M sub s term came out naturally. Woohoo! So score for Dirac. But anyway, M sub s was kind of the 4th quantum number to appear. It didn't initially pop in, but once it did, there's some really cool uses for it.
Any spinning electric charge creates a magnetic field. Spinning electrons produce magnetic fields with an identifiable magnetic polar orientation, so-called north or south. The polar orientation of a given electron is determined by the direction of its spin.
The real-world application, arguably, of M sub s has to do with how electrons spin. And in the video I just showed, the electron on the left was kind of spinning this way. All right, like if you were looking down from the north, it would look kind of like it was going clockwise. But the other electron was spinning in the opposite way. So again, if you were looking straight down now, it would look like it was going anti-clockwise. And electrons do this as well. And a spin 1/2, which is represented by the electron on the left, is a little bit lower energy than the spin on the right, which is the spin of negative 1/2. It's not a huge difference in energies between positive 1/2 and negative 1/2, but it is something that's important. And believe it or not, this can lead to the magnetism that's observed in atoms and ions. So along with M sub s, and along with the fact that there's only 2 electrons per orbital, we're going to talk a little bit here about magnetism because this is a result of the spin quantum number. In a diamagnetic system, you have electron spins that are canceled out. So remembering that electrons are spinning, and they either spin clockwise or counterclockwise, or as we're going to start talking about, up and down. If you have just as many up spinning electrons as down spinning electrons, we refer to this as diamagnetic. And a diamagnetic system doesn't have a magnetic moment, which means it's not a magnetic material. And most of the substances in our day-to-day life are diamagnetic. However, you can have an excess, if you will, of electrons which aren't canceled out, as in the diamagnetic system. So the lower left picture there, each of those arrows represents an electron that's spinning without something to cancel it out. And if you have a net imbalance, if you will, of electrons spinning one way or the other, up or down, works very well for this discussion, then you have what's called a paramagnetic system. And paramagnetic systems are actually small magnetic fields. All right, and they're a result of the electron spinning in one direction without something canceling the spin in the opposite direction. So in the diamagnetic systems, the ups and downs cancel each other. In paramagnetic system, you have a net number of ups or a net number of downs, whatever, that's spinning without anything to balance out. And that actually leads to some magnetic behavior. Ferromagnetic substances are like super paramagnets. And if you've ever played with little magnets and stuff, a paramagnetic material is something that approaches a ferromagnetic material, but it's not quite there. So if you have a true ferromagnetic material and you apply an external field, all of a sudden each one of the little individual paramagnets rises up and orients itself with the field. So in this picture, the black line represents an external magnetic field, and all those little randomly distributed paramagnetic systems all of a sudden now are all aligned to the top. And if they're all aligned in the same direction, all right, and if you take away the field, if that maintains itself, that's when they have then these super paramagnetic materials. And these are the kind of magnets you see picking up paper clips like on the right and stuff like that. Permanent magnets are just magnets, are magnetic systems that once you apply the field and you take the external field away, the magnet still maintains. And there's only a couple of substances that will do this well. Iron, of course, is one, and nickel, and a couple other ones. But a lot of systems are paramagnetic, and we're going to talk about how to find out if an atom is paramagnetic or not, and then maybe make some suggestions as to when it could be ferromagnetic or even a permanent magnet.
Different materials have different magnetic properties. Liquid nitrogen is diamagnetic and is not attracted to the magnet. Liquid oxygen is paramagnetic. Paramagnetic substances in the liquid or solid state are generally attracted to magnetic fields. Liquid oxygen is held by the magnetic field.
This is kind of a cool video to me. Those two substances, which are both very cold, by the way, you'd have to have them much colder than room temperature. Anyway, the first one was liquid nitrogen, and liquid nitrogen is a diamagnetic system. It's not attracted to a magnet. So that black thing there was called a permanent magnet, really strong, but you put liquid nitrogen through and it flows on through, kind of like water would, if you will, like you'd think water would. But the second substance was liquid oxygen. And liquid oxygen, we're going to see in future lectures, is a paramagnetic substance. And paramagnetic substance will be attracted to magnetic fields. So while the nitrogen just flowed on through, if you will, the liquid oxygen actually stuck between the heads of the paramagnet, or the permanent magnet. So paramagnetic substances are very important. And there's a lot of uses for these. And in a day-to-day body, people talk about sometimes free radicals in the body and how free radicals can cause you to have colds and disease and aging and all this kind of stuff. Well, free radicals are just another term for paramagnetic substances. And if you have a paramagnetic substance running crazy in your body, you could have some issues. They can detect paramagnetic substances pretty easy. The diagram at the top there shows an electromagnet, like that black thing in the last video. And if you have a paramagnetic substance in that glass tube and you turn the magnet on, you can see how the pink substance goes more into the field as you go off and on. So the magnetic substance is actually attracted to the magnet. You can also then do things with angles down here. The lower right-hand corner shows some iron 3 oxide and stuff. So there's lots of ways to measure if something is paramagnetic that aren't too difficult. But again, if you had a diamagnetic substance and you turned that electromagnetic on, it would just sit there, no interaction. Same thing in the lower right. If you had a diamagnetic system and you applied a magnet, it would also just sit there. So it's a real interesting phenomenon when it comes to these substances. When all four quantum numbers are put together, here they are, n, l, and m sub l. And let's review real fast n, l, and m sub l. N is always a whole number starting at 1, and in theory it goes up to infinity in whole numbers. Never negative, never 0, etc., etc. Subshells have an n dependence. So as we saw in the last section, for example, when n equals 1, then l can only equal 0. L goes up to n minus 1. But if n equals 2, then L will be equal to 0 and 1. There are two possibilities. So you'll have multiple subshells in a given shell under the right circumstances, and this is similar to how you can have multiple houses on the same street, I guess. Anyway. M sub L, the orbital, depends on L. M sub L goes from negative L to positive L. And so M sub L depends on L, just like we saw L depends on N. So if you had an L of 1, M sub L would be negative 1, 0, and plus 1. If L was 2, M sub L would be negative 2, negative 1, 0, plus 1, plus 2, etc., etc. So those three are all kind of connected. Electron spin, the new player on the block, M sub S, has only two values, and those are positive 1/2 and negative 1/2. And those correspond to, if you will, orienting up with the magnet or orienting down with the magnet. There's no dependence on NL or M sub L. They're only positive or negative 1/2. So keep that in mind while we go through M sub S. Here's a question. It says, which of the following is not a valid set of quantum numbers? And this is something that we can talk about now because you can see how the patterns go. And it also helps to learn how the different quantum numbers work. Again, n has to be a whole number from 1 up to something big. All of those n's are okay. L can't be bigger than n minus 1. So if you look at D, for example, n of 3, L can't be bigger than 3 minus 1 or 2, and that's okay. In this problem, all of the L's are okay. They're no bigger than n minus 1. Now, M sub L depends on L. M sub L has to be between negative L and positive L. So if you look, for example, at B, L equals 5, M sub L could be anywhere from negative 5 to positive 5, and having a value of 0 is an acceptable answer, like we saw in Chapter 6, Part 1. So in this problem, all of the M sub L values are okay. However, as you can probably see, M sub S, as we talked about, can only be positive 1/2 or negative 1/2. Answer D here is not going to fly. No M sub S of zeros. You can have positive 1/2, negative 1/2, no zeros, no anything else. Wolfgang Pauli, came along to the scene, and they started putting all the quantum numbers together. And he came out, long story short, with an idea called the Pauli exclusion principle. And the Pauli exclusion principle states that no two electrons in the same atom can have the same set of 4 quantum numbers. So what this means is that when you're putting electrons around atoms, each electron has to have its own set of quantum numbers. And I use the idea of an address. If I wanted to invite Joe but not Bill to my party, all right, I could know Joe's address. I don't have to send an invitation to Bill. All right, that's kind of sad. I apologize, Bill. But anyway, you get the idea. Each electron has to have its own address too. So if you want electron number 7 to come, but not electron number 9 to your party, then in theory you could use the 4 quantum numbers to distinguish electron 7 from electron 9. It's pretty clever what he came up with. Let's look at some examples of this. Now, in Chapter 6, Part 1, we looked at N, L, and M sub L. And when N equals 1, L, which can be no bigger than N minus 1, has to be 0. And M sub L depends on L, negative L to positive L. So if L is 0, M sub L can only be 0. And we saw how when N equals 1, L equals 0, this is a 1s orbital, all right, because N is 1. When L is 0, you have S. That's the stupid people driving freaking gas hogs, or whichever version you want to use. So if you can have only 2 electrons in each orbital, the 1s is an orbital. And so we can actually assign now the 4 quantum numbers. And 4 electrons in the 1s orbital, you can have n equals 1, L equals 0, M sub L equals 0, and M sub S equals 1/2. And you can have n equals 1, L equals 0, m sub L equals 0, m sub L equals minus 1/2. So the first set of quantum numbers was electron number 1's address. The second set of quantum numbers was electron number 2's address. And again, Pauli exclusion principle just says that each electron has to have its own set of 4 quantum numbers. So as long as we don't have any more electrons with those exact quantum numbers, we are good to go. So what you've just done there is you have figured out the electrons in the quote-unquote 1s2 filled electron shell. If that means something to you, cool. And if it doesn't, don't worry, we'll talk about that in a little bit. But again, what we're doing is we're putting individual electrons in the orbitals, and we're seeing how they worked out. So the s orbital, we're going to see, can only hold 2 electrons. When n equals 2, we saw that L can be 0 or 1. L goes from 0 up to n minus 1. 2 minus 1 means a maximum of 1. So there are 2 subshells on the n equals 2 shell. And again, it's like 2 houses on the n equals 2 street, while on the n equals 1 street, there was only 1 subshell, 1 house. But anyway, I digress. Now, the lower right-hand corner there, it has the different electrons possible and their quantum numbers for the 8 electrons that goes inside. So let's look at the first 2 right here first. All right, those are n equals 2, L equals 0, m sub L equals 0. When L equals 0, m sub L can only equal 0, so there's only 1 allowed m sub L. And like before, m sub S can be positive 1/2 or negative 1/2. So these first 2 electrons are the 2 electrons going to go in the 2s orbital, or the 2s subshell, if you will. The next ones now are when we start playing with L equals 1. Now when L equals 1, m sub L goes from negative L to positive L. So that means negative 1, 0, and plus 1. Now up until this point, we've only had one value of m sub L, and m sub S could be positive, negative 1/2. But now we have 3 m sub L values, negative 1, 0, and plus 1. And these kind of correspond to the x, y, and z axis, like we saw in chapter 6, part 1. But anyway, each of those m sub L's can have 2 possible m sub S values. So you can see the first 2 there are the 2 electrons going in when m sub L equals negative 1. The next 2 are for when m sub L equals 0. And the last 2 are for when m sub L equals plus 1. This type of orbital is the 2p. Remember, when L equals 1, that's p. When L equals 0, that's s. L equals 2 is d, etc., etc. So what this means is if you count these electrons up, there are 6 electrons in the 2p orbitals. You could also say that the 2p subshell holds 6 electrons. Each of the m sub L values is a subshell, or an orbital, excuse me. So there are 3 orbitals, 2 electrons per orbital because of the m sub S, total of 6 electrons in the 2p subshell. So for the n equals 2 shell, you've got 2 electrons in the 2s, 6 electrons in the 2p, 8 electrons total. And again, we're giving each electron its own set of quantum numbers, which is kind of cool. Oh, but there's more. When n equals 3, we start getting into the 3D systems. But like before, when n equals 3, L goes from 0 up to n minus 1, so 0, 1, and 2. And like before, there's a 3S system when L equals 0. There's a 3P system when L equals 1. But now we have a 3D when L equals 2. And as before, we can break all those quantum numbers down. Here are the 2 3s electrons. Right to there represents the 6 3p electrons. And then finally, you've got the 10 3d electrons. Notice the patterns. Quantum chemistry and quantum physics is just filled with patterns. 2 electrons per s orbital, 6 electrons per p, 10 electrons per d. Notice there's a gap of 4 electrons between those numbers. We're going to see this pattern continued. When all is said and done, the n equals 3 every shell is going to have 3 subshells, the 3s, 3p, and 3d. The 3s subshell has 1 orbital for 2 electrons. The 3p subshell has 3 orbitals for 6 electrons. And the 3d subshell has 5 orbitals for 10 electrons. There are 18 electrons total in the n equals 3. Oh, but you can keep going. Here's n equals 4. When n equals 4, L goes to 0, 1, 2, and 3. Remember, you go up to n minus 1. So now we have an F player. And again, like before, 2, 6, 10 for the S, P, and D. And you guessed it, the F, the next one will have 4 more than the D. So it's going to have 14 electrons total. So again, like before, here's all these different pieces. All right, here's the 4S to number 8 is the 4p. The rest of them in that column there are 4d, and now in the lower right, 4f. And you can keep going and going and going. But nowhere in all of these slides we've seen have the quantum numbers been repeated. And that's the idea behind Pauli exclusion principle. You have to have each electron have its own set of quantum numbers. We're going to do it this way, which is really cool. Now, on a practical level, notice here how all of the S systems, whether it's 1s, 2s, 3s, etc., they've all held 2 electrons. And the p system, the p subshells, because of their 3 orbitals, have always hold 6 electrons. And the d's hold up to 10, and the f's hold up to 14. This will help us later on. This is an overview of some of the things that are possible. The left-hand side shows the electron shells, 1, 2, 3, 4. And again, we went up to just 4 and stuff like that, but you could keep going. Then it shows the letters associated with them. Notice that there's a G for 5 and even an H for 6. There's also stars next to them. We haven't really seen those yet and stuff, but maybe one day. Anyway, then it says total number of orbitals available. If you have the L value, the number of orbitals equals 2L plus 1. If you have just the shell number, the n squared value will tell you the number of orbitals. Number of electrons, maximum electrons per the shell. And here's another little shortcut. 2n squared is going to equal the number of electrons for the shell. So there's different kind of things here and stuff, and figuring out how these work is part of your goal for this section. It's not hard. It's also kind of cool to remember that we're looking at the results of some calculus calculations here. And it's a little bit strange, but it is arguably easier than the actual math used to figure out these quantum numbers for electrons, stuff like that. Whoa, kind of trippy. Next question comes, how do you assign electrons to atoms? Like, do they go in random or is there an order? Well, there's absolutely an order. All right. Back in the days of Bohr, which we talked about in chapter 6, part 1, Bohr saw that the energy of the different places where electrons go is basically has just an n dependence. He saw that energy equals minus RHC times 1 over n squared. H is Planck's constant. C is the speed of light. R is the Rydberg constant, which you don't have to know / memorize, but it is a constant. So on all of those, the energy really just has an n dependence, and that worked great for hydrogen and the helium plus 1 ion. But when you have more than one electron, Bohr's rule doesn't work very well. And it's basically safe to say that when you have more than one electron, the energy depends not on just n, but on n and L. So the so-called n plus L rule is just the fancy version of what Bohr did. And instead of having just an n dependence, there's actually an n plus L dependence. So we're going to be using a lot the SPDF letters, and using those letters to find the L rule. If we add the L to the n value, the lower n plus L will be filled in first, and the higher n plus L will be filled in last. The picture on the left there shows what happens when you have like just a hydrogen atom. And because in a single electron atom, the energy depends just on n, you can see that 1s would be filled in first, and then 2s and 2p would be filled in essentially at the same time. There's no preference. And all the 3s would be after that, and the 4s and stuff like that. But once you have more than one electron, that's when you need the n plus L rule. And the N plus L rule is pretty important, all right, because this is what scientists, what chemists use to tell the order of electrons in an atom. And you can actually go through and figure out the N plus L values and go from lowest to highest, or there's other ways to do it we'll talk about here in a little bit. But in current theory, the N plus L rule works really well for assigning electrons to atoms. If you do have two values of N plus L that are the same, and we'll see examples of this. All right, so for example, 4s and 3p are going to have the same N plus L value. The lower N is filled in first, and the higher N would be filled in last. So 3p would be filled in before 4s, and we'll see this here in a little bit. This is kind of a cool video.
In a single electron atom, hydrogen, subshell energies depend only on the subshell's principal quantum numbers. In a mini-electron atom, the presence of electrons in one subshell affects the energy of other subshells. Consequently, the subshells are not filled simply on the basis of the principal quantum number.
The N plus L rule assumes what's called 0-point energy, which is the lowest energy state possible for an atom. Most of the time in the real world, because of like energy from the sun or nuclear radiation or any kind of reason, sometimes you have excited states, but we're going to assume that everything is behaving itself basically and pretty chill. So we're going to talk about then how we can predict the default energy system for the different atoms. And it works out pretty well. This is called an Aufbau diagram that we're looking at right here. Aufbau comes from a German word which means building up. And supposedly Bohr and Pauli in the 20s and stuff started figuring this out. There's different ways to write Aufbau, and you can do it any way you want. But what you want to do, I'll make like a cheesy one here. You start off with 1s, 2s, 3s, 4s, etc., etc. Then you skip one and go up to the right, and you start with the p's. So 2p, 3p, 4p. Then you skip one, go up to the right, 3d, 4d, and then the next one would be 4f. And you can keep going higher. But notice these arrows that go through it, all right? Those arrows are the configurations that you'd fill in the electrons. So this diagram obviously is better than my cheesy diagram. Here's the N plus L equals 1. Now, for 1s, remember L equals 0, so 1 plus 0 equals 1. 1s is always going to be the orbital filled in first. And N plus L would be 2. 2 plus L equals 0 for S would be N plus L equals 2. That's the next one to get filled in. Now, both 2p and 3s have the same N plus L. If you figure it out, they're both equal to 3. Lower N filled in before higher N, so 2p gets filled in first, and then 3s. The next group there is what we talked about earlier. There's 3p and 4s. They're both N plus L equals 4. Lower N before higher N, 3p before 4s. Now notice though that 4s in the fifth arrow there, if you will, does get filled in before 3d, and that's kind of interesting at first, but this is a result of the N plus L rule. Now, why this is important is that those arrows literally show how you fill in electrons. You're always going to fill in the 1s first, and the 2s will follow, then 2p and 3s, and 3p and 4s, etc., etc. And that's really, really cool. You can use N plus L numbers to figure that out, or you can just follow the Aufbau diagram, and either way is fine. But obviously, when you're putting electrons in systems, this is where it is. Now, again, if you've dealt with these kind of things before in the past in other chemistry courses, you might remember that, for example, carbon is 1s2, 2s2, 2p2. Cool. Carbon is 1s2, 2s2, 2p2 because there are 6 electrons. The s orbitals, as we saw earlier, always hold 2 electrons. P's can hold up to 6. So if you have 6 electrons total, the s's hold 2, so 1s2, 2s2, and then 2p's hold up to 6. Carbon has only 2 more electrons to go, so that's why it's 2p2. Hopefully it's starting to come into focus a little bit. But again, the goal is we're going to have very exact energy diagrams for how the electrons are placed around atoms. This is going to be the next step, is how do you write atomic electron configurations? And earlier I said for carbon 1s2, 2s2, 2p2. If that's Greek to you right now, please don't worry about it. What I'm referring to here is what's called spectroscopic notation, sometimes called SPDF. And we've seen here, for example, the NL notation. So on the lower right corner there, it says 1s1. Again, the number is the N that starts it off. The letter corresponds to L. S means L equals 0, P means L equals 1, etc. And the new thing now is the number of electrons, which is given as superscript. So 1s1 would be the electron configuration for hydrogen. Hydrogen has one electron. Remember, the 1 on the periodic table means one proton. That's the atomic number. But in a neutral atom, one proton would have one electron. So neutral hydrogen atoms would be 1s1. If you want to go one more to a 1s2, no problem at all. 1s2 would be the electron configuration for helium. Now, helium has 2 electrons total. 1s's can have up to 2 electrons. So 1s2 would be the SPDF or spectroscopic notation. Now, sometimes you're going to see these listed in what's called orbital box notation. This orbital box there with a 1s and a square and an up and a down arrow, and don't worry about the color coordination. But anyway, that's another way to write 1s2. And notice the up and the down. Those correspond to the positive 1/2 and negative 1/2 values for m sub s. Spin is basically how electrons spin around, either clockwise or counterclockwise. Pretty cool. So 1s2 would be the spectroscopic notation way of saying what the electron configuration is for helium. On the other hand, you could have an orbital box notation. You'd have literally a box with a 1s under it and 2 electrons. Sometimes I will just write the line under it, and I'll write arrows that look pretty cheesy, something like that, but they're all the same thing. There's going to be a reason why orbital box notation is pretty handy. This is kind of the overall view of how electrons get placed in. And in chemistry, like all the physical science, all right, it's always about the energy. So on the left-hand side, it says order of filling. That's really the energy distributions here, how we go. 1s is always the first in, 2s is next, 2p, 3s, 3p, 4s again before the 3d like we talked about earlier, but then 4p, 5s, etc., etc. We're going to use these to figure out the atomic electron configurations of atoms. One thing that's going to be somewhat helpful to us eventually too is to know where the blocks are on the periodic table. Now, remembering that s orbitals can only hold 2 electrons and p orbitals can hold 6 and d's can hold 10 and f can hold 14. The left 2 columns, which for this discussion also includes helium, by the way, those are called the s block elements. So 1s2, like we saw hydrogen was 1s1 and helium was 1s2, they're filling in, those are the outer electrons of that system. So they call that the 1s region. 2s is under it, and we're going to see 3s is there. The right-hand 6 columns, starting with boron and working over to neon and basically going down, those are called the p block elements. So s is on the left, P's on the right. We're going to see the D's are in the middle, and the F's are the lanthanides and actinides at the very bottom. So the actual order, the way the periodic table is configured, has a result of the electron configurations, which is kind of interesting too. Let's say that I said, write the electron configuration for lithium. All right, cool, no problem. So lithium is a group 1a metal. Its atomic number is 3. And then if that means 3 protons, and assuming this is neutral lithium, which it is, that would be 3 electrons total. And when you put the electrons in, you always start at the bottom of the Aufbau diagram and move your way up. So 1s2 would be the first part. And remember, 1s's and 2s's and and 3s's can only hold a maximum of 2. So once the 1s is filled, the third electron in lithium would go in the next one, 2s1. So 1s2, 2s1 would be the electron configuration for lithium. And notice that if you take those superscripts and you add them together, that should equal the total electrons. So 2 plus 1 equals 3. That's a nice way to kind of check yourself. Now, in terms of orbital box notation, you can write it this way. 1s at the bottom, 2s by itself. There's one orbital for each of the s orbitals, so that's why there's one box. On the other hand, the p's, the 2p and the 3p, there were 3 orbitals possible, so that's why they get 3 blocks. But again, 1s2, you've got an up and a down in the 1s, so that house is filled, but 2s has just a single electron in it. And you can write it up or down, it doesn't matter, but the important part is that up or down doesn't have the corresponding arrow in it. So lithium is actually a paramagnetic atom. It has an odd electron, an electron with an up without a down, or if you want a down without an up. Most chemists will write up first and down second, but really it doesn't matter. There's an odd electron running around, and that makes lithium paramagnetic. Beryllium is the next one. Atomic number 4, 4 electrons total. Always start with the 1s, so 1s2 fills that up, 2s2 fills that one up, 4 electrons total. So notice how we're literally starting at the bottom and moving our way up. Remember, s's can only hold 2, p's will hold 6, but in this case we filled up both 1s and 2s, 4 total electrons. If you do the orbital box for this one, 1s2 and 2s2 are both filled. Notice here how the ups, each up has a down, or each down has an up. Beryllium is a diamagnetic metal. It is not attracted to magnetic fields. So lithium does have a paramagnetic effect. Beryllium, on the other hand, does not. The s's are filled, each up has a down, no attraction. Boron is the next one, atomic number 5, so that's 5 electrons in the neutral atom. And like before, we're going to start with 1s and keep working up. So just like beryllium had 1s2, 2s2, the first 4 electrons, boron will also be 1s2, 2s2, but it has a 5th electron, and the next one to get filled in is the 2p. So boron, 1s2, 2s2, 2p1. This is our first p element that we've seen. So the orbital box notation, we would have 1 electron in that 2p. It does not matter which of the 3 boxes you write it in. People usually will do left to right, but it doesn't really matter. The goal is just to put it in there somewhere. And because there's an odd electron, that makes boron paramagnetic. So lithium paramagnetic, beryllium diamagnetic, boron paramagnetic. Carbon is the next one, just one past boron. It has 6 electrons total, atomic number 6. So like boron, it's going to start with 1s2, 2s2, and it has 2 more electrons to go outside of that. So that's going to be a 2p2. But there's a little bit of a twist here, because there's different ways you could put the 2 electrons in the 2p. So as an example, you could have, remember that the 2p's have 3 orbitals to them. You could put 1 electron by itself in the first one and 1 electron by itself in the second one, which would make it paramagnetic. But you could also put both electrons in the same box like that, making it diamagnetic. So what we're running into here is something called Hund's rule. And Hund's rule, there's the picture of Hund, basically realized that electrons wish to be in their own orbital first and only pair them up after there's no more room. So for this problem, what that means, carbon will not have the paired electrons like I drew right there. It's going to look something like this. And that's what we're seeing right there. I use the analogy of if you've ever lived in a house with like a brother and sister, and if there wasn't room, like you could share a room with your brother and sister. It's not impossible, but it's awkward. Like if you want to put a poster up of a rock band and they like country music, then it's kind of awkward, okay? It's better to have your own room, but it's totally possible, all right? Well, electrons are kind of the same way. Electrons would prefer to have their own room if possible, but they can pair up, be in the same room if they need to. There's a little bit of an energy of putting two negative electrons in the same orbital, the same basic space around the atom. So Hund's rule is basically a way to minimize the energy of it. Hund's rule again just says put electrons in their own orbital whenever possible and only start pairing once there's no more room. So carbon is paramagnetic. It is not diamagnetic, even though you could draw it that way. A diamagnetic carbon would take more energy than a paramagnetic carbon, thanks to Hund's rule. Nitrogen has one more electron than carbon, so it's 1s2, 2s2, 2p3, 7 total electrons. And again, remembering Hund's rule, each electron goes in its own room until there's no more rooms possible, so nitrogen's definitely going to be paramagnetic. You can see there the 2p3, each electron in its own room. Each electron has its own space. They can put up their own posters in their room, whatever you want to say. Nitrogen, paramagnetic. However, the next one, a little bit more interesting. Oxygen, one more electron than nitrogen, all right? So just adding one more electron, 1s2, 2s2, 2p4. Remember that p's hold up to 6, so we still got some room. 8 total electrons possible. However, at this point now, the extra electron, the 8th electron, you have to put it in with something that's already there. So in this case, the 2p system, one of the orbitals does have both an up and a down electron. The other 2 electrons are still by themselves, but in this case, there is no more room in the in, if you will. The electrons have to start pairing out. So one of the orbitals is diamagnetic, if you will, while the other 2 orbitals in 2p are paramagnetic. So oxygen is paramagnetic, like we saw. Fluorine has one more electron than oxygen, 1s2, 2s2, 2p5. Remember, p's go up to 6, so we still got some room. 9 total electrons. We're going to pair one more of those electrons. There's the orbital box diagram showing the 2p5 part. Fluorine definitely paramagnetic. Neon, which finishes off this row, has 10 electrons total, 1s2, 2s2, 2p6. And at this point now, we've added up electrons to all the downs. So every up has a down electron. Neon is a diamagnetic element. We've reached the end of the second period. The second shell is totally filled. And all of the elements in group 8A, we're going to see, and this includes helium too, by the way, have diamagnetic shells. There's no more room left. Notice too that most of the atoms we've seen have been paramagnetic. So if you have to guess if an atom is paramagnetic or diamagnetic, you should probably guess paramagnetic. The ones on the ends of the shells, like neon here or beryllium, are going to be diamagnetic, but most of them are paramagnetic, at least in their raw form. So this is kind of an overview of what we just saw of boron through neon. And again, the first ones were all very paramagnetic. Hund's rule says don't pair them up, all right? But you do start pairing when you get to oxygen. It takes less energy to put a 2p electron in as a paired electron than it does to do the 3s that we'll look at here in a little bit. So again, all of them are paramagnetic except for neon, which is kind of cool. Sodium, group 1A again, but 11 electrons total. So for this one, we're going to have just one more electron than we did for neon. So it's going to be 1s2, 2s2, 2p, thanks for playing, 1s2, 2s2, 2p6, 3s1. Or you can probably tell that it takes more and more syllables to talk about these electron configurations. So the 1s2, 2s2, 2p6 is really nothing more than neon with a 3s1 on top of it. So I'm going to introduce at this point what's called noble gas notation. And if you want to use noble gas notation, you can absolutely use it. If you're going to use noble gas notation, you must use square brackets. The noble gas goes in the square brackets, and what goes past the noble gas goes outside. So instead of saying 1s2, 2s2, 2p6, 3s1, you can say a neon core 3s1, and that's obviously less writing, less syllables when you're talking about things and stuff like that. So noble gas notation can be super helpful. Another thing that's interesting, all group 1A elements have a core neon, a noble gas core NS1 configuration. We saw lithium earlier was 1s2, 2s1. So lithium is really like a helium 2s1 configuration, and you can see here how sodium is a neon 3s2. Potassium, right below it, if you want, you can look at this, is argon 4s1. So notice how N is changing. 2, 3, 4. That number comes from the period number. If you look just to the left, that's the N number. This is kind of a cool way to figure it out. This also explains why all of the alkali metals, which is group 1A, why they all have similar reactivity. That one electron on the outside is ready to rock and roll. The number of N does change with the noble gas, but it's got some kind of noble gas inside, and then you've got that extra electron on the outside. Pretty cool. Aluminum, we're skipping magnesium. Aluminum has 13 electrons total, so it's got the 1s2, 2s2, 2p6, 3s2, 3p1, or you can just write noble gas notation, highly recommended, neon in brackets, 3s2, 3p1, which I recommend, paramagnetic, all that kind of stuff. Here's the electron configuration, what it looks like. 3p1 is all by itself. All of aluminum has the aluminum group, the twisted metals, has some kind of a core NS2 NP1. Now, some of them have some d electrons. We'll see that here in a little bit. So it doesn't work quite as well for the twisted metals as it does the alkali metals, but it is kind of a nice pattern to see. This is why a lot of the groups have really similar patterns of reactivity due to their similar electron configurations. Phosphorus, group 5A, 15 electrons total, 1s2, 2s2, 2p6, 3s2, 3p3, or neon 3s2, 3p3, which is highly recommended. 3p3 means there's 3 individual electrons because of Hund's rule once again, so very paramagnetic. All of the pnictogen group 5A elements have some kind of a core, ns2np3. Some of them will have some d electrons. I'm warning you about that. We'll see that in a little bit, but they do have similar outer electrons. That's why their reactivity is also similar. Chlorine's electron configuration is one of these right here. And the question is, which one is it? And that's a really good question. There's a couple of ways to answer this question. First of all, you can just look on the periodic table. Chlorine is number 17. And if you add up the number of electrons in the superscripts, you want to look for one that has a 17, all right? And I think that the only one that does that is B in this list. So if you add up the 2, 2, 6, 3, 5, that actually comes out to be 17, and that would be one way to answer this question. A second way to answer this question, you know that chlorine has 17 electrons because of the periodic table. You could follow the off-bow diagram through 3s2, 3p5. That would be another way to confirm the answer B is correct. And yet another way is that chlorine is part of the P block of elements. The 6 columns on the right of the periodic table are all called the P block. It's the second set of P electrons. The third period would be 3p, and your 5 electrons into it. So for example, argon to the right would be a 3p6, sulfur to the left would be 3p4. Anyway, any of these ways you can figure out then the answer B is the correct configuration, 3s2, 3p5. Remember that 3s's can only have 2, so that one's not going to fly. The other ones I think are at least okay. 1s2, 2s2, 2p6, 3s2, 3p6. Answer D would be argon. E would be calcium. C, 1s2, 2s2, 2p5. That would be fluorine. The S blocks, P blocks, D blocks, F blocks can be really helpful. And we're going to talk about the Ds and the Fs here pretty soon. But for the S's and the P's so far, it makes it really easy. And again, reactivity of electrons and elements is a lot of times dependent on where you are in the different groups. So knowing that the S's are the 2 blocks on the left. And by the way, helium here should be an S block. That's an incorrect animation. But anyway, the right 6, not including helium, P block. The middle ones there are the Ds, and the Fs are the lanthanides and actinides at the bottom. Transition metals, the ones in the middle of the periodic table, are the ones that have the Ds. And if you use an Aufbau diagram, or if you just figure it out, the D electrons pop in after the S ones. And we talked about earlier how 4s gets filled in before 3d. So transition metals have some kind of noble gas core, and then there's a period number, so like 4s2, and then n-1 means 3. So, for example, if you wanted to know the electron configuration of titanium, Ti number 22, it has an argon core, it has a 4s2, and the n comes from the period number, which is 4, to the number to the left of that whole group, and then n-1, 4 minus 1 would be 3. And titanium is the second of the transition metals in that period, so that would be a little y value number of electrons of 2. We're going to see that the d electrons are really important for transition metals. So sometimes transition metals are called d block elements because it's the d electrons which affects a lot of their reactivity. But for right now, just realize that they all have some kind of noble gas core. They're going to have some s electrons put in first, and then after that they're going to have Ds. But the S's and the Ds, there's this n-1 dependence on the Ds. All right, it's 1 less than the S's. Here's just some examples. Potassium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, or argon 4s1, and that's obviously a lot easier. Calcium, 1 more electron than potassium, would have an argon 4s2, and that's not too bad. Now, scandium is the first of the transition metals. It's in the 4th period, and 4 minus 1 means it's going to be filling in the 3d electrons. So notice there, scandium would be a lot like calcium, argon 4s2, but with a 3d1. Remember, Ds can go up to 10. All right, so there's 10 possible spaces, and if you count from scandium Sc over to zinc Zn, you'll see that there are 10 elements corresponding to the 10 3d elements. Titanium, we talked about earlier, argon 4s2, 3d2. The next one is vanadium, argon 4s2, 3d3. Now, chromium, you would expect, would be argon 4s2, 3d4. But for some reason, and even I don't know, and scientists don't know, one of the s orbitals, electrons, jumps ship, and it goes from a 4s2, 3d4 to a 4s1, 3d5. This is a break in the n plus L rule, and chromium is the first exception to our rule. So I point this out because I want you to know that science hasn't figured everything out yet. All right, it should be 4s2, 3d4 according to theory. In reality, it's 4s1, 3d5. I'm also pointing this out because all I really expect you to do in the Chem 200 series is to be able to predict electron configurations based on the n plus L rule. So if you put down for chromium argon 4s2, 3d4, I would give you credit for it. The actual electron configuration, argon 4s1, 3d5, maybe one day I'll talk about the theory developed by you that explains why this is 4s1, 3d5 and not 4s2, 3d4. But anyway, what are you going to do? Moving on, manganese, argon 4s2 3d5. Copper, skipping some here, copper is another exception to the rules. It's argon 4s1 3d10 instead of argon 4s2 3d9. And again, it's kind of an unknown mechanism. Just realize that these ones in red here, chromium and copper, are exceptions to the N plus L rule. And there are other ones too. As you get further down, the transition metals, lanthanides and actinides, there are some exceptions. I don't understand why, but it gives you 2 chances to be right. So, woohoo, score. Anyway, trying to make up for a scientific lack of knowledge. I know it's kind of silly, but anyway, hopefully you get the idea. Exceptions, obviously, and stuff here to what's going on, 2 chances to win. So for example, for chromium, I would expect you probably to just put down argon 4s2 3d4, but if you put down the actual configuration, argon 4s1 3d5, awesome, I'd give you credit for both. And the same for copper. Copper should be 4s2 3d9 officially, but for whatever reason, it's argon 4s1 3d10. And again, there are other exceptions on top of this. You'll see it in the textbook and stuff like that. Chromium, copper, and other elements don't follow the N plus L filling order, which drives me crazy as the instructor, but welcome to science. We don't always have everything figured out. People think it's instability associated with the D subshells. Maybe it is, maybe it's not. All I'd really like you to know is how to fill things in by the N plus L rule, and just realize there are some anomalies. And again, if you give me the answer, either the actual answer or the real answer, you're good to go. Lanthanides and actinides are similar to transition metals, only lanthanides and actinides, you're actually filling in the F electrons. So like we saw with the transition metals, the D block elements, you can find the N, the shell number, from the period, which goes left to right, and then N minus 1 was how you found the Ds. So for example, titanium we saw had an argon core, it was 4s2, and then N minus 1 would be 3d2 in titanium's case. Well, with lanthanides and actinides, you do the same kind of thing, but it's N minus 2. So if the period number was, say, 6, you would go 6 minus 2 to see that it was a 4F element you were filling in. There's 4 Fs for lanthanides and 5 Fs for actinides. We're not going to focus as much on the lanthanides and actinides. There are quite a few exceptions to N plus L rule, just showing here what it's weird. There's cerium and uranium as examples of how this stuff all works out. Lanthanides and actinides are pretty cool. There's a lot of neat chemistry going on there. And again, you can find the electron configurations after this class. It's just that we're going to focus more on the transition metals and the main group metals and nonmetals. This is, again, the electron configuration filling order. It's based on the Aufbau. Notice in the lower right-hand corner here, this is basically the periodic table telling you which ones you fill in. So 1s, as we saw, always first, 2s, and then follow the arrows to 2p, 3s, follow the arrows to 3p, 4s first, here's 3d, so 4 minus 1 is 3. Notice here how the period numbers 1, 2, 3, 4, 5, 6, 7, etc., etc. So 3d and then 4p follows, then 5s, n minus 1, 4d, 5p, then you go 6s, and then notice here how here's the first 4f, it's 6 minus 2 or 4f, then 5d, 6p, etc., etc. So this is an alternative way to see how the electrons get filled in as you go through. Here's just some things you can check yourself. If you'd like to pause them before I give you the answer, that's fantastic. But I'd like you to figure out, for example, the electron configuration for iron. And I would use noble gas notation just because it gets kind of crazy. Iron has an argon core, 4s2, 3d6. Cool. Now zinc is in the same line as iron, so it's going to look similar to iron, but it will have more 3d electrons. At the end of the zinc line, that's the end of the 3d region. So that's going to have an argon 4s2 3d10. All of the ones there in the zinc family are going to have a d10. So zinc was 3d10. Under it is cadmium. That would be a 4d10. Mercury under that 5d10, etc. etc., etc. Technetium is on the next row down, so it's going to have a different noble gas notation. It's going to be krypton, 5s2, and n-1 would be 4d, 4d5. And then niobium, Mb, if you keep going down, that's also a krypton, 5s2, 4d3. Osmium is on the next line down, so that's going to have a different noble gas. That's going to be xenon. Xenon, 6s2. Notice the 4f14. 4f always comes before the 5ds, at least for us right now. So 4f14 and then 5d6. And then finally, one of the brand new ones, Mitnerium, which is number 109. A heroine of mine, Lisa Mittner. We'll talk about her in Chem 222. Anyway, her configuration, or Mitnerium's configuration, would have a radon core, 7s2, 5f14, 67. And again, all I expect you to know is the expected N plus L rule. There are probably exceptions for some of these, but you just have to know the given ones and stuff. If you do report the actual configurations, that's awesome too. 2 ways to win. Making an ion from an atom and figuring out the electron configurations is actually not that bad. So let's talk about anions first, the negative ions. And an anion just has extra electrons beyond what the neutral atom would have. And adding electrons to make the anion is pretty easy. You just follow the normal N plus L rules of filling in electrons. So let's make the phosphide ion, which is P negative 3. So phosphorus is neon 3s23p3, but like we talked about, the 3 P's can hold up to 6 electrons. So when you make phosphide, you have an extra 3 electrons. Remember, phosphorus in group 5 minus 8 has a negative 3. The negative 3 means 3 more electrons, and they are just going to go in that 3p configuration. So phosphide would be neon 3s23p6 or argon. Notice how we went from a paramagnetic atom to a diamagnetic anion. A lot of the common anions and cations are actually going to be noble gas configurations and diamagnetic, which is kind of cool. So if you're making an anion, just add the electrons as if it was normal. All right, just add them using normal N plus L rules and you're good to go. Cations, the positive ions of the atom, all right, what you want to do in these cases is you're going to take away electrons from a configuration. And the rule is a little strange. I want to focus on that. You want to take it from the highest N, and if there's a tie, then you take it from highest N plus L. Phosphorus does make a positive 3 ion. It's rare, but it does happen. And to make a positive 3, you have to remove 3 electrons. So in this case, you could remove electrons from highest N. So if phosphorus has 1s2, 2s2, 2p6, 3s2, 3p3. But the highest N would be the 3s and the 3p. Those are higher than the 1 of 1s or the 2 of 2s and 2p. So we're going to remove the electrons from 3s or 3p, but there's a tie. All right, which of those 3s do we pull them from? So the second part there says if it's a tie, highest N plus L. Highest N plus L basically means that last one's in equal first one's out, but in this case, 3p would be higher N plus L than just 3s. So for either way, you want to take them away from the 3p. Phosphorus 3 plus would be neon 3s2. So again, on the left-hand side is neutral phosphorus, and the question is, where do you take away those 3 electrons from? And it's definitely going to be highest N, so 3s or 3p, but which one? So if it do have a tie, then you take it away from highest N plus L. So highest N plus L would be the 3p's. You can see that that's empty on the right-hand side. You end up with 1s2, 2s2, 2p6, 3s2. The electron configuration 1s2, 2s2, 2p6 represents which ions and or atoms. All right, and this is kind of interesting. Got sodium, got oxide, magnesium 2 plus, and neon. Well, let's start with neon. All right, so neon has 10 electrons. Its atomic number is 10. And if you put the electrons in, first electrons go in 1s, next electrons go in 2s, and then 2p. So 2 plus 2 plus 2s6, the superscripts of that configuration equal 10. Neon is 1s2, 2s2, 2p6. So at the very least, then we know that answer D here is legit. But let's look at the other ones. Now, sodium, neutral sodium, has 11 electrons. And neutral sodium would be 1s2, 2s2, 2p6, 3s1. But sodium plus 1 means we're taking away an electron. And you take it away from highest n, or highest n plus L. 3s is higher than 2s and 1s and the rest of sodiums. So the sodium plus, we're going to take away that 3p1. And guess what? Sodium plus 1 is also 1s2, 2s2, 2p6. So now you can see that at least A and D are correct. You're going to find here that all of these have the same configuration. So let me save you having to watch my bad handwriting and look at what's actually over here now. You can see that when all is said and done, they're all 1s2, 2s2, 2p6. So here's sodium. We're taking away that 3s1 electron to make it Na+. Let's go to magnesium here real fast. See, magnesium has a 3s2, but we're taking away 2 electrons. Highest N means take those away. Also 1s2, 2s2, 2p6. Oxide, which I saved for last, you're adding 2 more electrons. It has a negative charge. You're going to put them in the lowest unoccupied orbital first. 2p holds up to 6. Oxide also is 1s2, 2s2, 2p6. They're all the same electron configuration. A lot of the noble gas configurations are very common when it comes to main group ion charges. So the positive ones like sodium, magnesium want to be like noble gases, and the negative ones like nitride, oxide, fluoride, chloride, they also want to be like noble gases. Noble gas configurations are the cool kids in the back of the bus. All of the ions kind of want to be like them. Transition metals, when you're making an ion, and these will almost always be positive, I want to go back to the idea where you remove the highest n electrons first and then the n-1 electrons after. Now, before so far, when you've made a positive ions, it's always worked out that the last electrons in are the first electrons out. But you don't necessarily see that with transition metals. And let me show you an example. Iron, neutral iron, is argon 4s2 3d6. And the two most probably stable configurations of ions for argon are iron 2+ and iron 3+. Now remember, the rule is remove highest ns electrons first, and then after that, if there's a tie, go highest n plus L. Well, iron has 4s2, and 4 is higher than 3. So what that means is that the first electrons out for transition metals always the 4s2 or 5s2 for the next ones, or 6s2. So iron plus 2 has an argon 3d6. None of the d electrons were touched. If you make iron 3+, then you take away one of the d electrons, because then you've got a tie between 3d, 3p, 3s, etc., etc. I'm pointing this out because when it comes to transition metals, the last electrons in are not necessarily the first electrons out. So in iron's case, 4s came out before 3d, even though as you're filling the electrons in, the 3d electrons were filled in after the 4s, which is very wild. Here's orbital box notation. Our iron 4s2 3d6 becomes just 3d6 when you have the iron 2+ ion. And if you make, of course, iron plus 3, then you have 3d5. So again, always remove electrons from the highest n value first. And that usually means the s electrons before the d's you just finished putting in. Notice how the magnetism changes quite drastically. So for example, the iron and the iron plus 2 would both have 4 unpaired electrons, but iron plus 3 would have 5 unpaired electrons. Hund's rule, keeping all of them separate as long as you can. So iron plus 3 would be very paramagnetic. More unpaired electrons means more paramagnetic. And this is basically saying what I just said, so I guess I just couldn't wait. Anyway, the number of unpaired electrons as it goes up, the degree of paramagnetism also increases. All right, so here's zinc plus 2. We're removing the 4s electrons first because highest end before lowest end, but zinc plus 2 is diamagnetic. It has a 3d10 outside of the argon core, totally diamagnetic. On the other hand, iron plus 2 has 4 unpaired electrons, which does make it paramagnetic. Here's an example of manganese 2 plus. Manganese 2 plus, you remove the 4s electrons as well, and you end up with 3d5. So if I asked which of those ions was the most paramagnetic, you would say that manganese 2 plus was the most paramagnetic. Usually the more unpaired electrons you have, the more paramagnetic something is. And of course, zinc as a diamagnetic system wouldn't be magnetic at all. It would be the least paramagnetic or non-magnetic, something like that. Which ion corresponds to this configuration? So notice that there's no 4s electrons. All right, so this is going to be an ion because the 4s electrons get filled in first, but if they've moved away, then it's going to be taken out. And there's also some 3d electrons. And if you count them up, 2 in the first box, 4 in the second, 5, 6, 7, 2, 4, 5, 6, 7. This is a 3d7. Now, having an electron periodic table here can be super helpful. And what I'm going to do is I'm literally going to start counting at scantium, SC number 21, because scantium would be a 3d1. Titanium would be 3d2, vanadium 3d3, chromium 3d4, manganese 5, iron 6, cobalt would be 3d7. So neutral cobalt would have a 4s2 3d7 configuration. But because cobalt here in answer C has lost 2 electrons, that's going to keep the 4s orbital empty. So I'm going to argue that answer C would be correct. And if you actually figure out the values, here they are. One thing to note is that rhodium is actually on the next row down. Rhodium would have 4d electrons, but it wouldn't have an unfilled 3d set. Rhodium would have a 3d10 configuration. And of course, calcium would be just argon, stuff like that, which is crazy. Another thing too, rhodium is another one of the weird exceptions on the N plus L rule. Rhodium is actually krypton 5s1 4d8, fascist krypton. Up there I wrote it as krypton 4d6. All right, and again, either way, or neutral rhodium would be, neutral rhodium would, I wrote down as krypton 5s2 4d7. Neutral rhodium is actually krypton 5s1 4d8. This is again chemists' inability to understand totally what's happening. N plus L, which is what we are using, works pretty well most of the time, but there are some exceptions, fascists. However, as an ion, you could use either configuration and end up with the same result, which is also good. But that's neither here nor there. The important part is that you saw that in this problem, you had an argon 3d7 configuration. Because the 4s was empty, the 4s electrons had to be removed. And what I literally did is I just counted left to right from scantium 3d1 over to cobalt 3d7, and because that cobalt without 2 electrons would have an empty 4s, cobalt 2 plus.